Hi, this next one's called matrix determinant. Write a function that accepts a square matrix, n by n, two-dimensional array, and returns the determinant of the matrix. How to take the determinant of a matrix? It is simplest to start with the smallest cases. A 1 by 1 matrix is a trivial example. There's just one element, right? 1 by 1 meaning one row, one column. And the one value in there is the determinant. So easy enough. And then we have another sort of base case here, a 2 by 2 matrix. Consider A, B, C, D. You could imagine it visually like this. It has a determinant A times D minus B times C. That's how you calculate that. The determinant of an n by n sized matrix is calculated by reducing the problem to the calculation of the determinants of n matrices of n minus 1 by n minus 1 size. For the 3 by 3 case then, consider a matrix like this, A, B, C, D, E, F, G, H, I. Remember, these are just variable names. They'll be numbers when we're working with the actual matrices. The determinant is A times the determinant of A minor minus B times the determinant of B minor plus C times the determinant of C minor, where the determinant of A minor refers to taking the determinant of the 2 by 2 matrix created by crossing out the row and column in which the element occurs. And remember, it said n minus 1 by n minus 1 size. We started out with a 3 by 3, so we're going to grab a 2 by 2 section of it. And they were kind enough to put dashes in here. You can see this A, B, C is all gone, and the D and the G, right? They pretend you deleted this row and this column, the first column, right? And then you're left, you see, with the E, F, H, I. And then once you have this 2 by 2 matrix, right, they already told us how to handle these. This is how you calculate the determinant of a 2 by 2 matrix. So we can do that, right? There's sort of an implied clue here where it's talking about reducing the problem to the calculation of the determinants of n matrices of n minus 1 by n minus 1 size. It really hints towards using recursion, and so that's what I'm going to use. We haven't talked about that in this series, I don't think, so this probably isn't the best first video on it. There are simpler examples, but it's fine. Basically, recursion is when a function makes a call to itself. So you can imagine when we implement our code, at some point we're going to be calling determinant, you know, on something else in the code. And you may be thinking that looks weird, and it is kind of weird. You think, well, if a function's calling itself, how do you ever exit? And that's a great thought if you had that. That's why you need these base cases in here, and you have to make sure that your recursive function is updating in a manner that will get it to hit one of these base cases eventually. You may have one base case, you may have more, but you have to be progressing towards that, otherwise it's like an infinite loop. Not good if you do that. And so let's see, where were we? We're down to the 3 by 3, and then we're going to make, note the alternation. Yeah, that's another important note here. See how it was A times the determinant of A minor, then we had minus, and then for the next one it's plus. Those signs will keep alternating, minus, plus, so it's like positive, negative, positive, negative. So we'll handle that too. The determinant of larger matrices are calculated analogously, e.g. if M is a 4 by 4 matrix with first row A, B, C, D, then the determinant of M is A determinant A minor minus B determinant B minor plus C times determinant C minor minus D times determinant D minor. So you can see those alternating symbols. The odd numbered entries, you can think of it like that, are sort of added, and the even number ones are subtracted, their values. So you don't have to be an expert in or really know much anything about matrices to do this, so we'll go through it. Don't worry if you don't know that, you'll be okay. As usual though, go ahead and pause the video and try it out yourself, and then come back over when you are ready. So to start, I think this syntax is probably a little bit new here, where it's like an integer array. It's like two arrays, right? They call that a jagged array. You could search that term if you wanted some more information, but you can think of it like a two-dimensional array, and that's how we're going to make a matrix, right? You can think of it as, imagine this one down here, if we think of it as three arrays, right? The first one could be an array of three values saying ABC, then another array of DEF, and another array of GHI. So that's how that works. You pass it two indices. The first one could be the row, and the second one you can think of as the column. And so if you want to access an element, let's say the D in here, you could say row 1, column 0, and it should give you whatever number is in that D slot right there. So that's how that works. Feel free to grab more info if you need it. I'm going to start by noting the number of rows and columns in the matrix that they're passing in to us. And to do that, I'm going to say, let's call it numRows equals matrix.length. We know that's how to get the size of an array. And I'll say num columns will be equal to matrix 0, right? This is saying grab that first array inside. You can think of that top line I did, number of rows. The length is just saying how many rows are in this matrix. In this case, it's 3. And then number of columns, we'll say grab the array, the integer array at index 0, which is ABC, and give me the length of that. Now with these jagged arrays, technically they don't have to all be the same size. So maybe as a first step, you want to go through your matrix and make sure they are the same size. I'm going to add some protection against that, but it won't be full. So at this point, we got the number of rows and the number of columns. They should be the same, right? We're dealing with n by n matrices. So let's add one protection for that. We'll say if num rows is not equal to num columns, we'll throw that generic new argument exception. And we can give a message like, you must pass an n by n array. And you could list the values you found if you wanted to. Could be helpful for you. So typically with recursion, you'll enter your base cases, right? Those are so important. We got to be able to catch those. So I'm going to implement the trivial example and the 2x2 here and say, hey, if we're dealing with a 1x1 matrix, let's just return that one element inside, right? And it's kind of a shortcut for us too if we just have a matrix of that size. So I'll say if num rows equals 1 and num columns equals 1, we can just simply return the element, right? There's only one element. Return matrix 0 for the first array. There's only one. It's only valid index. And then the first element in it, index 0. Remember we use 0-based indexing. So just return that one element that's there. And that's an integer. So we're good. Problem solved. So then we get on to the second example, right? The base case. This would be for a 2x2, right? So what did it say to do for 2x2? We had to return A times D minus B times C. So we can access those elements in a similar way. We can say return matrix. Now what would, for A, what do you think would go there? Well, it's just like in the 1x1, right? It's the first element is going to be 0, 0 for A. So we have to multiply that by element D. How would you access D? Row 1, index 1, right? And then do the same thing to grab B. Say matrix row 0, element 1, that's the second column. And you'll multiply that by the value of C, C, we would say the first row, I'm sorry, the second row and the first column. Again, using that zero-based numbering. So that looks good. Those are all different. That should be A times D minus B times C. So cool. Good deal. That should cover our base cases. And if we want, we could even test and see and make sure it passes these first two tests, which should blow up once it gets to the 3x3, and that's fine. All right. Oh, I got to bring in system exception for that. Or system, using system. All right, let's see if we can get the first and second to pass. Yeah, and something else that might be helpful, let's just make a little, let's make a little log statement to console, all right, line passed in a num rows by num columns array, or I'm sorry, matrix. So that should give us a little bit more information there. So you can see, okay, pass in 1 by 1, we were fine. Pass in 2 by 2, we were fine. And then we hit this test failed on the third one, which is expected. That's fine. We haven't implemented it yet. So we'll go ahead and do that now. And instead of doing it in the general sense, maybe I'll do it for the 3 by 3 first, and then that'll show the pattern. And then once you recognize that, we'll do it in the general way, and then that'll be better for submission purposes. So the next thing I would say to do is to make a helper method that can get the minor matrix, right? That thing they were referring to in the instructions. Remember, we had a minor, right? And they were telling us how to get that. So if we make a method that can do that for us, that'll be very helpful, and we don't have to dump a bunch of code in this top method. So let's break that out into another method. Private static. So we're going to want a matrix, right? It's going to be n minus 1 by n minus 1, but still a matrix nonetheless. So this is how we're representing those for this problem. We'll call it get minor matrix. And for this, I'm going to pass an int row, an int column value, and these will let me know which rows and columns to essentially minus out like they did here, right? These are the values we want to skip. We don't want those. And then we need the original matrix that we're dealing with, right? The n by n one. So we'll say that. Okay, I'm going to do the same thing to get the number of rows and columns. It's relevant here as well. Okay, so we've got those. Let's create our minor matrix. So for that, I'll say int, not sure, I'll call it minor, and to make one of these, say new int, I give it the number of rows, and then just an empty set of brackets. Okay, so we've initialized at least minor. The next step, we're going to make a for loop. I'm going to do it nested, one to go over rows and one to go over columns, and sort of populate this new minor matrix that we made. And the idea is going to be is that I'm going to check the row and column value, and if they match with what was passed in as the parameters, then I'm going to skip that iteration of the loop, and sort of, so we don't get the values that should be crossed out, right? So that's going to be the strategy here. equals 0 is less than num rows plus plus. You know what? I might even name this row. A lot of times we use I, but a good rule of thumb is if you're going to have nested for loops, you can give them more meaningful names and it's a little bit clear. If you work with these a lot, I and J aren't bad at all, but you can imagine when you go 3 levels and stuff too, it can be a little ugly. And you know, we have this 2-dimensional array, which is why I end up with this nested for loop. One to iterate over all the rows, and then for each row I want to deal with all the columns too, right? So obviously we can't call that the same. We'll call it call less than num columns plus plus column. Okay. And so the idea for this is if row equals, oh, I apologize, I can't use row because I named the parameter row here, so maybe I will use the I and J. It's not so bad here. Or you could do some other variation on the word row if you wanted. So if I is equal to row, this is bad, right? This is like we don't want to access the value in this row. So we're going to use this keyword continue. If you haven't seen that yet, all it basically does is say you don't execute any more code below it. You essentially go back up to the top of the for loop and do your increment, your plus plus I, and then you try again. And you come in again and try and run through it. So that's all continue does. And that's what we want. We just want to skip processing if it's the bad row. So I'm actually going to make a separate variable for the row index that I will initialize to 0. And then minor row index. I can't count on I because I'll have a gap, right? We're going to skip over one of these and I want to start at 0 and increment. I don't want to go 0, 2, 3, you know, if imagine 1 were the bad row, the value 1, I wouldn't want to access my minor matrix by skipping one of the elements, right? So that's why I made a separate variable for that. So we do have to initialize. That was the catch. When I did this statement, it kind of initialized the jagged array, but each of the elements of this are an array itself, and so those all need to be initialized as well. So we'll do that here. We'll say new int num columns -1 because we're getting down to an n-1 by n-1 array, right? It's going to be one size smaller than what we were given. So, and for the same reasons, I'll make a column index that I made that row index, that we can have a consistently incrementing value there, since we're going to be doing some skipping in the columns. And for the same reason, you know, int here, I have to rename these two so I don't clash with the parameter names we use. The names have to be unique, right? So then we can say if j is equal to call, that's what we called that column parameter. Again, we want to continue. Just get out of here. Don't consider that value. And then at that point, we can, once we're past this, we're not dealing with a banned row or banned column. We can say minor row index, and then give it the column index. And we're going to say that equals to matrix, the original matrix, right? I, j, the row and the column value. And remember, the bad ones will be skipped because we said continue there. And then I had to increment this column index. It's not being incremented as part of my loop. You know, I just declared it out here. So I got to make sure that's doing it. You could make another line. Remember, this is just shorthand. So after my statement fires, it'll increment this, the value. So that's a nice shorthand, but you could break it out to another line if this just looks confusing to you. So at that point, I suppose you could write whatever kind of print statements in here you wanted if they were helpful. We'll see. If I run into a bunch of trouble, we'll add that. And then for the same reason I had to increment this column index, after we've finished processing the whole column, right? We want to increment the row index too. And so I use the prefix operator here because there's no other work going on, so it doesn't really matter. You could use it before or after. When I can use before, I do it before. So that should populate our minor matrix, and then I think at that point, once we've been over all of the elements, we can simply return minor. Should be okay. See if this helps. So yeah, we're going over all the rows. Consider it's going to start with the first row, that top row, and then we're going to process all of the column values. You know, you can imagine all of the column values for the first row, and then, you know, you can imagine us doing the columns from the left to the right. That's sort of what we're doing here, skipping when we need to. So I would recommend making another helper method that could help. I made one to print matrix. So you can see that you're sort of populating these the right way, right? Because we're working kind of blind here. If we're in the IDE, we could kind of step through this and make sure it's doing what we want. But I'll say this. We'll pass that jagged array. And I should save. I forgot to give it a return type. We need that. And so we can say int numRows is equal to the matrix dot length. Nothing new there. We've done that twice already. And then we can iterate over that. Int I less than numRows plus plus I. Int array row equals matrix I. Grab the first row or whatever you're at, and I'm going to make some text for it. Row and then we'll print all the row values out. And no, row, I called it. Row vals plus equals, we're concatenating, right? And I'll put a comma. We'll get a comma with the last one, but this isn't for, it's only for our own help, so who cares if there's an extra comma at the end. You can add logic, you know, you could have checked the size, and if you're on the last one, don't add a comma at the end, but I don't really care that much at this point. And then finally, console write line row vals. And so it'll go through each row, sort of print out the elements for you. And so this is handy, so you can make sure that you're making the minor matrix right, you know, it can be pretty helpful. So we've got that. We've got something to make a minor matrix. So let's go ahead and take on this 3x3. You don't have to, you can go right into the general solution right now, but I thought this might be helpful to visualize it. So now we're tackling that 3x3 matrix, right? So for this one, we'll go back to the instructions and follow sort of what the process was that they spelled out there. So Where was the 3 by 3? Where was the 3 by 3 here? There we go. So the determinant is A times determinant A minor. And we now have a method to get the minor, so that's good. That'll help us. So we'll kind of run with this. I'll start by saying return matrix 0, 0, that's A, right? And then we'll say times determinant, which is the name of our overall method, right? This is where the recursion magic is happening. We're going to invoke the same method again, and we're going to use our method to get the minor matrix, right? Because it said the determinant of A minor. So for that one, we'd pass the row and column of A, right, is 0, 0, the first row in the first column. That's why I'm passing the 0, 0 there. And then we have to give it the original matrix too, and then it will make it down to that n minus 1 by n minus 1 size next. So that covers this first term, right? A times determinant A minor. So now we'll do the next one. We'll say minus, I'm going to tab here just to make it a little easier to read. Let's go ahead and grab B. What would the indices for B be? 0, 1, right? Times, I'll go ahead and copy this. Get minor matrix. This time we got to use 0 and 1, right? B would be in column 1 using 0 base numbering. So that'll cover, that's the second line I wrote matches this, right? B times determinant of B minor. And then and notice I had the plus sign on the previous line, right? We're alternating between minus and plus. So now I'm back to plus, and we'll add the line for C. Matrix 0, 2, right? 2 would be in, or I'm sorry, C would be in the last column. This would be 0, 1, 2 times determinant of the minor matrix 2, the original matrix. And that covers us for the 3 by 3 case, right? That was the line they gave us. So we're good here. And the problem is, though, we're not going to keep writing out num rows equals 4 and num columns equals 4. And then, you know what I mean? You just couldn't do it. You can imagine if you tried to do all those, it would just be ridiculous. So then the idea is that let's see if we can find a pattern here. First, I'll run the test. Let's make sure that all this stuff is even working first. Okay, so the local tests must have just been up to size 3 by 3. Maybe I'll add suppose I could add something to print. Let's add a statement. Print matrix. And so you could see, oh, yeah, the print didn't work. I probably forgot. Yeah, sure did. The $sign here. See, it was just using the literal curly brace and curly brace test. We'll expand that, and then you can see the values here, right? So this is helpful. 2, 5, 3, 1, negative 2, negative 1, 1, 3, 4, right? So this can be helpful for you if you're having trouble. You know, you can print out, you can call the method to get the minor matrix that's associated with the matrix and then print out that minor because it's just a matrix too, right? So you can use that print method however you like if you're having some trouble. So anyways, we got to get this so it works in the full sense, right? If I hit attempt, it's not going to work. There's certainly going to be something that's a 4 by 4 or larger and I'll do that just to prove it. I mean, they got to. Yeah, I mean, we failed. Look at that, a 4x4. So, okay, come on. The game's over. We can't just keep going 3x3. But I was hoping by writing it out this way you would see the pattern here. And what is the pattern? Let's look at each line. The 0 is always the same, right? Then these are increasing from 0, incrementing by 1. And then the same pattern here in our get minor matrix. So let's think if we can generalize that, right? What if we made a for loop and sort of added these up for the appropriate number? So I'll try that. I'm going to comment this out. We're not going to use it. We're just going to have one generalized solution here. Okay, so I'm going to make a variable result. Remember, this whole function is returning an integer value. And I'm going to accumulate as I go. I'll initialize it to 0. You could probably use a link method here to aggregate or sum. I'm sure there's a clever way of doing that. But I'll just do a simple for loop here. So for and call equals 0. Call is less than num columns, I believe we called it, plus the column. Okay. And so we know we've got something going on with the alternating subtraction, addition, subtraction, addition. So we'll handle that. We're going to have a check in here. Remember how to check for an even or odd number? That was modulo 2 equals 0, right? If it's equal to 0, you're dealing with an even. If it's equal to false, or I'm sorry, if it's equal to 1, then you're dealing with an odd number. So in the case of an even, this plus equals, we're going to add to our running total. And what did we say above, right? The matrix, the first index was always 0, right? And then the column number, though, increased, right? So isn't that precisely what call is doing in our loop? So what if we throw that val in here? And then times determinant we saw above. And we had get minor matrix, right? And then again, the 0 was sort of fixed, right? And then we see these column values incrementing. Same deal, just like we did back here. So let's give it the 0, call, and then the original matrix, right? And then notice I used the plus equals for even values. So else, it's either even or odd, right? That's it. What if I copy this whole thing, and now we need to subtract the result, right? So instead of plus equals, what if we go minus equals? That should match, right? That should be the same as this thing up here. But the nice part is that the number of columns can now grow. It's dynamic, right? So let's go ahead and try this. See what we get. Execution timed out. Code timeout. You know what? I'm going to remove some of this printing stuff in here. Let's get rid of that guy. I think we had some other ones. Print matrix. Am I still calling print matrix anywhere? I don't. Oh, yeah, let's not do that. That was just to help us debug, right? That's a lot of extra work that we don't need to do. So yeah, let's clean that up. Exit, test failed. So I might need my debugging. Let me see what I did wrong here. But it looks like all my values are coming out as 0. So what did I do? Result equals 0. Call module 2 plus equals 0. That looks okay. Oh. Wow. Okay. It's like so I did all that awesome work and then I returned 0, right? Just like was left in here. How about if we actually return the result that we have? Sorry about that. There we go. That looks a lot better. And that's the way it goes sometimes in this business. You just something dead stupid simple right in front of your face, and you'll look at it for a half hour and wonder what the heck is wrong. So yeah, okay, we passed it. I think I got rid of all the clutter. I'll leave the method in. It's not being called. That's fine. I'll get rid of this part. We didn't need it, but sometimes doing something like this helps you out, right? It was a lot easier to visualize than trying to do it all in your head. So maybe you write it out on scratch paper. You can use this code space as scratch paper. But yeah, it helps you generalize things. See the pattern, right? So you can generalize it. They're going to make us run this again because I've technically modified the code. Got our base cases. Yeah, we don't need that anymore. Looks pretty good. And yeah, there's probably a more elegant way of summing these up, like I said, with a link method, but I'll attempt this again. If it's still green, I'll submit that. And we'll call this challenge wrapped up. Cool. Green. Let's submit it. Get those points. 368. Nice jump. So yeah. Looks like they did something like we did with the little helper method to get the minor matrix. Covered their base case there. Pretty cool. So yeah, feel free to look through those. Otherwise, I will call this a wrap. I'll see you in the next one. Thanks for watching.